Hello everyone, I am Sina Saber Hakpava, and in this video I'm going to show you that if we are given a network surface or any kind of NURBS surface which I have in the left, what should we do if we want to create a solid topographic model out of that network surface? It might be useful if, for example, you are an architect and this network surface is the 3D model of your project site. So let's just start. I'm going to first talk a little about what topography is and how it works. About topography, this photo is a good example. Here you can see some green curves on which a number is written, 30, 20, 10, and so on, 50 or whatever. These numbers are the height of these curves, the distance, the vertical distance between each of these curves and the reference plane that I'm just showing with this arrow. So this is our explanation about topography. Each contour is a curve, is a closed curve whose points are exactly at the same height. For example, this one's points are exactly at the same height of 30 meters above this reference plane. So this is all we need to know about topography, and let's head back to Rhino. Before we go any further, I need to mention something. It's up to you what the interval, the vertical distance between your topography contours is. In this particular model, it is half a meter, but it's really something that is up to you and the project you're doing. So now let's first do what we want to automate manually so that we get a sense of what it's gonna be like. First, I'm going to create a horizontal surface, a horizontal plane, to be more precise. Then I'm going to clone it. I'm going to use the array command to create a lot of it. For example, 15 I guess would do, and for example half a meter, but it's really up to you what the vertical distance between these is. So now we have some horizontal planes. We need to get their intersection with our 3D model, which is buried. Here it is. If I use the intersect command in Rhino, it gives me the intersections. So these are my topography contours, half a meter away from each other vertically. So now we're going to do the same thing in Grasshopper. We are going to automate it. But let's get started. First, we have to bring this network surface into Grasshopper. Then we have to make those horizontal planes, horizontal surfaces whose intersection with this network surface we got earlier. So in order to do that, I first build a bounding box. Then I need the height of this bounding box. In order to do that, I I'm going to get each of these corners of this bounding box. I get their height and I get the maximum and minimum height from them. The algorithm I'm going to write is going to do what I explained. So let's do it. Deconstruct. These are the heights of the points, the corners of the bounding box. If I just use the bounds component, it's going to give me the minimum and the maximum. You can see it. This is the minimum, this is the maximum. I use the construct domain to get access to this these numbers. So what do these numbers mean? They mean that if I create a surface at the height 0, as the minimum height of the bounding box of this network surface is 0.11, all of this network surface is above this horizontal plane that I've just created, because its height is 0 everywhere. And on the other hand, if I create another horizontal plane at the height 4 meters, all of this network surface is below my second horizontal plane, because its height is 4 meters everywhere. So these two horizontal surfaces contain my network surface. I can literally just turn these into integers, but something bad might happen, and because I guess it rounds. Now it's fine, but in order to be safe, I'm going to make this domain a little bigger than what it already is. For example, I bring its minimum to -1 and bring its maximum to 5 to be safe. I mean, I would like to do something like this, but inside grasshopper. Now you see the height of this downer horizontal plane is -1, and this upper one is 5 meters. So let's get started with it. I'm going to do as I told you. I'm going to remove those, and I'm going to subtract 1 from the minimum height and add 1 to the maximum height. I hope I did it correctly. Yes, and then I'm going to turn them into integers. The reason that I didn't give anything to this input is that there is some default input here, which happens to be 1 and the thing I wanted. So from now I'm going to create my planes. I use the component XY plane. XY plane gets a point for input, so I'm going to construct a point. Let me just print it here. It really doesn't make much of a difference what you give it in the X and Y inputs, but For the Z input, you need to give the minimum height. If I hide this one temporarily, we see that it created our first horizontal plane. I need more of it. I can use the series component. I can cut this and leave this be for now. I'm going to create a list of the heights of my horizontal planes, which starts at this minimum -1 number. Well, so this is my start. My step is well, you're free to choose whatever you want. I'm going to choose half a meter. That was the interval of our default model we had here. Same as this model, I'm going to go with half a meter. So, and I'm going to reach the maximum height of 5 meters. Well, there is something we need to discuss here. We are going to go from -1 to 5 with half a meter steps, half a meter long steps. How many steps should we take in order to go this entire distance? The answer is we need to subtract these from each other, and then we're going to divide the length, divides the overall length, the overall distance between minimum and maximum to the length of our step, which is half a meter, and it gives us 12 steps, so we have to take 12 steps to make it, and it seems fine. It's just half a meter away from our destination, so I'm going to add one more step to it. There we go. There we go. It works pretty fine right now. So these are the heights of our topography planes. Topography horizontal planes. We have it. Now we can unhide. No, actually we don't need to unhide that. We unhide this one. We want to get the intersection between this network surface and the planes that we just made. So the component for that is surface split. Before we go any further, I'm sorry, I need to tidy things up a little around here. Well, this looks much better. It gets two inputs. The first one, the upper one, is my surface, which is here. The other one is oh, I'm sorry, it's not surface split we have to use right now. It's brep and plane intersection. Here it is. The first thing it gets is a brep. We give it our network surface. The second thing it wants is the planes by which we want to cut our surface. So it pretty much did it. And we can also, I brought this here. We can also change the vertical distance between our topography contours, topography curves. Let me select it to demonstrate better. For example, I can put this to 1 meter. Or 2 meters. You see the number is dwindling. So now we're good with this part. Well, this component which gets the intersections for me gives me an error. I really couldn't figure out what's wrong with it, and it seems to me that it's working fine. So I just left it be for now. Right now, I returned this to its default number, half a meter. So we are going to go to the next step. We are going to split our network surface with our topography contours. Surface split is the component we must be looking for. We get the curves. I should flatten these curves first. And we get our original surface here. And it would take a little while to work. Well, I guess it managed. Now we have 101 segments from this network surface. I'm going to make them planar. Right now they are not planar. They are still curve shaped. So in order to create planar surfaces out of them, we need to use a scale non-uniform. We must scale this if I give 0 as an input to the Z input of this component, it flattens these segments. It something like projects them on a horizontal plane. But right now I'm not going to connect it here. First, I need to take care of this plane input. It gets a point. It can get a point from me. What I'm going to give it is, first I'm going to create a bounding box for all of these segments. Then I'm going to explain what I'm going to do. I'm going to get one of the corners of each of these bounding boxes, which has the minimum height. For example, this one, or for example, this one. The ones with minimum height, I'm looking for them. In order to do that, I'm going to take a look at here. I'm going to sort these points, based on their height. In order to do that, I need sort, give their height as the key and the points themselves, and then I have it. Of course they were sorted to begin with, I guess, but it doesn't hurt to be safe. And I'm going to get the points with minimum heights and flatten them. Well, we have 101 points here, and there we have 101 surfaces. Then the amount of these points and those surfaces match, therefore we can do this. And I guess we managed to accomplish what we sought to do. Let me just see what happened. Let me hide this one. It didn't work. Sorry, wait. Oh, I forgot to attach this 0. Well, it works correctly right now. Well, let's finish it all. For now, we're going to extrude the surfaces that we created so far. For their extrusion distance, I'm going to give 0.5 meter, which we had here. I'm going to extrude them 0.5 meter down. So I'm going to extrude them minus 0.5 meter. I take these here. I give this to the extrusions input, and it would take a little while to complete. Well, it seems that it finished doing its job, so now we can bake it, and it would take a little while again. Well, it finished, so we can turn the preview for these components off, and we have what we wanted. There are just 2 issues I have to address. First, in the hills and pits, these surfaces with local minimum heights or local maximum heights, because we used the bounding box component, it doesn't behave the way it should be. We should filter these surfaces out and deal with them separately. This algorithm that I wrote here doesn't work for these correctly. This is the first issue. The second issue is that if I get the type of these geometries here, they're usually closed BREP and closed extrusion, but among them are some open BREPs as well. If I use create set, I can see that. Oh, sorry, I need to first open extrusion. This is not something we would like. It has the potential to mess up things a little bit. This is an example of it. This is an open extrusion, and they're a little problematic, and we should look for them and eliminate them. You can use a Python filter to do so. I try to correct these issues and put the corrected grasshopper script in my GitHub. You can access it. The link to it is below this video, and I really thank you for watching and giving me your time.